A rigid uniform annular disk is pivoted on a knife edge A in a uniform gravitational field as shown, such that it can execute small amplitude simple harmonic motion in the plane of the figure without slip at the pivot point. The inner radius r and outer radius capital R are such that small r square is equal to capital R square by 2 and the acceleration due to gravity is g. If the time period of small amplitude simple harmonic motion is given by t is equal to beta into pi into under root capital R by g, where pi is the ratio of circumference to diameter of a circle, then beta is equal to. We need to round off the solution to two decimal places. Let's look at the solution. We are given with a couple of relations which are small r square is equal to capital R square by 2 and the time period of simple harmonic motion, which is capital T, is equal to beta into pi into under root capital R by g. Let us consider small m as the mass of the given annular disk. The area of the given annular disk can be written as A is equal to pi into capital R square minus small r square. Mass per unit area is written as m by pi into capital R square minus small r square. Let us consider an elemental annular disk at a distance x from the center of gravity point having a thickness dx as shown in the adjacent figure. Then the mass of the element considered is written as dm is equal to m by pi into capital R square minus small r square into 2 pi x dx. Upon simplification, we get dm is equal to 2m by capital R square minus small r square into x dx. The first step is to find out the moment of inertia of the angular disk about the center of gravity point, which is written as dm into x square, which is 2m by capital R square minus small r square into x dx into x square. The moment of inertia about the center of gravity for the considered elemental annular disk as 2m by capital R square minus small r square into x cube dx. Now, upon carrying out the integration on both sides, we get the moment of inertia about the center of gravity as integral small r to capital R 2m by capital R square minus small r square into x cube dx. From this integral on the right hand side, 2m by capital R square minus small r square can be taken outside the integral, and upon simplification, we get the moment of inertia about the center of gravity as 2m by capital R square minus small r square into x power 4 by 4 with the limits small r and capital R. Upon substituting the limits and simplifying, we get the moment of inertia of the disk about the center of gravity as m by 2 into capital R square plus small r square. Here we can make use of the given relation, which is small r square is equal to capital R square by 2, and upon substituting and simplifying, we get the final moment of inertia of the given annular disk about the center of gravity as 3 by 4 into m capital R square. The second step is to find out the moment of inertia of the disk about point A. Using the parallel axis theorem, we get the moment of inertia about point A as the moment of inertia about the center of gravity plus m into small r square. Substituting ICG is equal to 3 by 4 into m capital R square plus m into capital R square by 2, we get the moment of inertia of the disk about point A as 5 by 4 into m capital R square. Now, the third step is to find out the time period of the oscillation about point A. Let the disk be disturbed by an angle theta in the counterclockwise direction about the hinge point as shown. The configuration of the disk is shown in the figure at that particular instant when it is disturbed by an angle theta in the counterclockwise direction. Then at that instant, an inertial torque I theta double dot and the torque due to the weight of the disk acts about the hinge point. Then the equation of motion of the system at that instant can be written as I theta double dot plus mg r sine theta is equal to 0. It is to be noted that moment of inertia I in this equation of motion represents the moment of inertia of the disk about the hinge point A. That is, substituting I as 5 by 4 into m capital R square, theta double dot remains the same, plus mg into r is written as capital R by square root 2, and sine theta becomes theta for smaller amplitudes. Then, rearranging the terms in this equation of motion, we get theta double dot plus mg into r capital R by square root 2 divided by 5 by 4 into m capital R square is equal to 0. Simplifying this, we get the equation of motion of the system as theta double dot plus 4g by phi into square root 2 capital R is equal to 0. Then the natural frequency of the oscillation can be written from this equation as omega n square is equal to 4g by 5 root 2 into capital R. Taking square root on both sides, we get omega n is equal to 2 by square root of 5 root 2 into under root g by capital R. Recalling the natural angular frequency, which is omega n is equal to 2 by under root 5 root 2 into under root g by capital R. We know that the time period of oscillation can be written as t is equal to 2 pi by omega n. Substituting omega n and simplifying, we get the time period of oscillation as t is equal to under root 5 root 2 into pi into g by capital R. We are given that the time period of oscillation is t is equal to beta into pi into under root r by g. On comparing the above two equations, we get the value of beta as beta is equal to under root 5 root 2, which is approximately 2.66. The accepted answer range for this question is from 2.62 to 2.70.